deterministic. We just have a single action that we would take in a particular state. Right? Maybe we always show this one ad to a particular customer. Or we could have a stochastic policy where we rank it. So this would be something like, oh, when this customer shows up, I show, a vacation ad or I show a board game ad with 90% probability versus 10%. Both types of policies are really common, and it can depend in part what sort of domain you're in and whether you're trying to learn that experience. Okay, so let's see what that would look like in this case. For bar server, you could say that no matter where it's in, it'll be as you right. That's a little policy. It just requires you to specify that every single state what state you would take or what is the distribution of. So in this sort of setting, we're normally conditioned to make,
So it's like making like a statement. In like words, like switch to like different as well as like different state goals, which like check the back state, different state. The same way like in learning like functionaries. Can you do that?
We're writing. So great question. It will in general we're learning it'll change its policy over time. So it started with the other policy, and then over time it was more lots of policies and trying to search for things good. It's a great question, and it relates to what I was saying here. Two of the central functions we're going to talk a little bit about at the beginning is evaluation and control. Evaluation says someone gives you a fixed policy, and you want to know how good it is. Like maybe your boss says, hey, I think this is the right way to advertise to customers. We're going to make a lot of money. You go deploy that achievement decision policy, and you see how much money you make. So that'll be evaluation. Control is you actually want to find the best. And so in general, to actually find the best policy, we're going to have to do a lot of trial and error. We want to do that in a strategic, efficient way, so we can quickly learn from that. So in general, we're going to be talking about things. I just want to highlight because we build up the complexity in terms of the type of policy. So we're going to be thinking about both like planning and control, and sort of thinking about how complicated it is. So we're going to think about evaluation and control, because evaluation is often itself part of doing control. If you know how good a policy is, you may be able to improve it. Both planning and learning. In planning, we're going to assume someone gives us that dynamics model and that reward model in the state and action space. We're just going to try to find a really good policy. And in learning, we're going to actually have to control the decisions we make to give us information that allows us to identify. So what we're going to start with is sort of the simplest of the settings. We're going to assume that we have a finite set of states and actions. We're given models of the world. Leads down for this. We want to evaluate the performance. And think of this really as so to think about this, then build up to MVPs. So let's say you're always to down data samples. Good. Plus 1 and 10 in estimates, plus 1, 0 in all other states. In this case, this is where we start to see the ideas that are going to be really useful for decision synthesis, which is we can start to think about how good particular trajectories are. So we're going to have a horizon, and you're going to see this in your homework too, which is the number of time steps in each episode. It could be infinite, or it could be finite. Like basically how many time steps do you get to make decisions. And the return, which we're going to call GT, is just going to be the discounted sum of rewards from the current time step to the end of the horizon. And the value function in this case is just going to be the expected return. In general, this is not going to be the same as the actual return unless you just have a deterministic process. Because the idea is that you're going to have stochasticity in the trajectories you reach, and because of that, you're going to get different. So you might wonder, should we be able to for why these systems wane really rewards more than one is that it's just mathematically really convenient. I hope it's not to infinity, particularly if we have infinite number of steps we make. And it's there is a discount factor. That's the way to true rewards, then we get rewards. So true for organizations too. And if the absolute lengths are always finite, you can always let's say use gamma equal 1. You don't have to make a large discount. But when you have infinite horizons, it's generally important to make this number 1, so your rewards number 1. Part of it is really hard to compare infinities, so it's hard to say like this reward that is we will start to talk about how we actually use the value, or check the markable process, and start from there. Okay, thanks. So, my partner, go to the whole one. So, my wonder.
help me sell. Honestly, most curly hair doesn't need to be straightened anyway. If you grow it out a bit, you can make a fun big hair style. Big hair not only makes your hair look fuller, but you can also shape it into cool style. Like this guy, who styled his hair into a heart shape. And crazier yet, when he swims, his big hair even acts like a little cushion. So whether you keep it curly, style it big.
Faster comes in, faster goes out. Oh my God! What did you do? Let's get out of here! Daddy thought, whatever you done, keeps fun. I think it's almost like
Literally, I went you. I also spent that's a couple of years.
For slow rise, being able to do this requires 7 essential exercises. First, your hips must be free.
Enjoy your lunch. Take it quick.
Week 4 of the thermodynamics course. So previous week we saw on first law and also some problems on pure substances, how to solve water pure substances, how to solve those. This week extending it to two phases when the substance is no more in a single uniform phase like air and gaseous phase, but you have two phases, liquid and vapor, and they are getting converted and so on. How to solve those. And also some problems relating this two-phase substances in applying first law in processes. So with that, let's start for this week. The first one, it's a propane. Again, is some problem on pure substances. So propane in a steel bottle of volume of 0.1 meter cube has a quality of 10% at a temperature of 15 degrees Celsius. Use the generalized compressibility chart to estimate the total propane mass and to find the pressure. So this is the compressibility chart which is given at we are at 0.2. My ZF, which is the fluid compressibility, liquid compressibility is 0.035 and gas compressibility is 0.83. Using this, we need to find out what is the total propane mass and what is the pressure. So to start with, so critical pressure of propane is 4250 kilopascal and temperature is 369.8 Kelvin. So your reduced temperature in this case is T by Tc. So temperature of 15 degrees is 273.15 plus 15 divided by your critical temperature 369.98 gives you a temperature ratio of 0.78. It's a reduced temperature. So for this state, we know at PR sat is 0.2, which is given. So P is PR sat into critical pressure. So with this we can find out the pressure. So that comes out to be 850 kilopascal. So with this, the overall compressibility factor now becomes Z is 1 minus X times of Z of liquid plus X times Z of gas. X is your vapor fraction or the vapor or gaseous fraction. So this comes out to be 0.9 into 0.035 plus 0.1 into 0.83 gives you 0.1145. So with this, R is now for gas constant is 0.1886 for propane. So using now ideal gas equation or the compressibility equation PV equal mz RT, you get m is 13.66 kg. So first, a gas bell is submerged in liquid water with its mass counterbalanced with rope and pulley as shown in figure. The pressure inside is measured carefully to be 105 kilopascal and the temperature is 21 degrees Celsius. So a volume increase is measured to be 0.75 meter cube over a period of 185 seconds. What is the volume flow rate and the mass flow rate of the flow into the bell, assuming it is carbon dioxide gas? So breakdown. So you have a bell which is submerged in liquid water and there is an opening here. So mass of carbon dioxide, you are pumping some carbon dioxide inside which fills the space in the volume, and if the pressure increases it will try to lift the bell up. The whatever gas is inside, it will exert a pressure upwards along with the buoyancy force, and that is balanced by your mass here and the weight of the bell. So what we are saying is initially the pressure is 105 kilopascal and the temperature at that condition is 21 degrees Celsius, and you are seen that the volume which is increased is 0.75 meter cube with a period of 185 seconds. So with this we can find out the volume flow rate. Once we have found out the volume flow rate, we have to find out the mass flow rate next. So we'll see how to solve this. So first, the volume flow rate is your change in volume with respect to the time. So dV by dt is delta V by delta t. So what you get is 0.75 meter cube, which is the rise in the volume in 185 seconds. So 0.75 divided by 185 gives you 0.004054 meter cube per second, which is the volume flow rate of the carbon dioxide. Now we know that mass flow rate is m dot is rho into v dot, so or v divided by specific volume. So we need to find out density or specific volume. So we'll use the ideal gas equation. So m dot is p into v dot by RT. So we know p is 105. We know v dot, or if you even if you can write it as m dot equal to p v dot by RT, or you can estimate specific volume and density. You get p equals to rho RT, or p specific or p into specific volume equals RT. So that is p by RT is your density. So that gives you the mass flow rate. So m dot is p into v dot by RT. So here p is 105 kilopascal and the volume flow rate which we have estimated divided by you have to be careful here is 105, it is in kilopascal, so into 10 power 3 divided by R, which is 0.1889 which is in kilojoule per kg, so that will 1000 will cancel out. into temperature, which is 273.15 plus 21, which comes out to be 0.00766 kg per second. So everything was given, straight away found out volume flow rate, and then we estimated density to calculate the mass flow rate. The other parts of the questions were redundant. So next question, determine the phase or phases in a system consisting of water at the following condition and sketch PV or TV diagram showing the location of each state with respect to saturation lines. For this we will require steam table. So what is asked is determine the phase or phases in system consisting of water at the following condition and sketch it in a PV or TV diagram showing the location of each state. So at 5 bar and 151.9 degrees Celsius. So in that case, I'll just share. So this is the saturation table for water. So what we have been asked is to find out the state at 5 bar and 151.9 degrees Celsius. So if you go to the table, saturation temperature of water, and this is given in temperature, and you will also find it in pressures as well. So you want to put it in pressure. So saturation temperature in terms of pressure. So you have pressures listed here, the one which are in bold black, and so corresponding value, this is 5 megapascal. Sorry, we wanted at 5 bar, which is 0.5 megapascal. So we need to go to 0.5. So 0.5, the corresponding your temperature is 151.831. So that is your saturation temperature corresponding to this pressure. So, and the question says you want 5 bar and 151.9. So that is your saturation temperature. So this can exist at any state. Your water liquid temperature till the vapor, because it's a pure fluid, it will boil at the same temperature. So you can have saturated liquid or saturated vapor or a mix of both. So with just 5 bar and 151.9, it can be in any of the states. So next is 5 bar and 200 degrees Celsius. So in case of 5 bar and 200 degrees Celsius, so your saturation temperature is 151.9. So but this temperature is greater than your saturation temperature. So in that case, what will happen is if you're starting your water at 151.9 degrees Celsius, and you keep on heating it. So the liquid water will fully convert into vapor, and we will have vapor at 151.9. Then then if you keep on heating it again at constant pressure, you will reach 200 degrees Celsius. So what you will have now is a superheated state. So we have steam, the superheated steam. So the state of B will be at superheated steam. Then the second question, third question is 2.5 megapascal and 200 degrees Celsius. So we need to go to 2.5 megapascal. You see 2.5 megapascal and 200 degrees Celsius, to find 2.5 and 200. So here your saturation temperature is 223.95. So your temperature is lower than the saturation temperature. So in this case, what happens is it will be in a liquid form. It's a subcooled liquid. So it's just like a normal room temperature water. Even though it boils at 100 degrees Celsius, your room temperature water is around 30 or something. So this is similar to that. So it's a subcooled liquid. The next question is similar to locate 4.8 bar and 160 degrees Celsius. 4.8 bar and 160 degrees Celsius. Say 160. So when in this case, this is similar, just like the previous one. It will be in the subcooled liquid. So to see if your pressure, if you are looking at a constant pressure, if your temperature is more than your saturation temperature, you will have superheated vapor or superheated steam for water. If your temperature is saturation temperature, so for a given pressure, if you temperature is of the liquid or vapor mixture is a saturation temperature, so either it can either exist as saturated liquid, saturated vapor, or a mixture of liquid and vapor. You can have any of this combination. And the third part is if you have at constant pressure, if the temperature is lower than the saturation temperature, then it exists as subcooled liquid. So those are three, and you can do it the other way around with pressure. So for a given temperature, you have corresponding saturation pressure. So if the pressure is more than the saturation pressure, then it will be in liquid form. Here that's the difference. The temperature, for a given pressure, temperature is greater than, it will be in vapor, superheated steam. But for a given temperature, if the pressure is more than saturation pressure, it will be in liquid form. And if the pressure is lower than the saturation pressure, it will be in vapor form or steam. And same, if your corresponding Tsat, if the mixture is in Psat, your saturation pressure, then it can be either vapor, liquid, or both. I hope this is clear. And we need to represent it in a PV or TV diagram. So how will that look? So if you take this is your P versus V, you have a two-phase dome. So this line to the right, so line to this right is your vapor phase line, and to the left is your liquid phase line. So if you draw a constant temperature, this is your at constant pressure P set for a given temperature. So when you are existing in T set or P set, this represents your saturated liquid, and the right point represents the saturated vapor, and anything in between is a combination of two that is a two-phase case, and whatever x your determine is your vapor fraction. So that determines how much amount of saturated vapor is present. And in the first case, where T set 5 bar and 151.9, so that presented your saturation case, and the second case was 5 bar and 200 degrees Celsius, where it existed as a superheat. So a constant temperature line will look like something like this. So in the second case, where for given 5 bar, your temperature is more than 151.9. So this will be T equal to 151.9. The second case, what will happen is the temperature is more than this thing will be different, more than 200. So for a given pressure, you will lie somewhere here. So this is your superheated vapor. So your pressure is same. So I am at 5 bar here. This is 5 bar. So for same pressure but a different temperature. So this now lies at superheated case. So similarly, you can draw this for as a TV diagram. So similarly, TV diagram will also look like this, but instead of that, you have pressure lines, something like this. This is a constant pressure line if it's a 5 bar line. So 5 bar 151.93, 151.9. So that is your saturation point. So this is your saturated liquid, and this is your saturated vapor, and anything in between is your two phase. And the second case was 151.9 and 200 bar. So now that will lie here, which is 200. This is a constant pressure line of 5 bar. So this is your superheated steam. So that's how your PV and TV diagram will look. And similarly, for the other cases, you have a different pressure, and in the instead of superheated, in the subcooled case, it will be on the left hand side, something on the left hand side. So that's your subcooled liquid. And similarly, in the PV diagram, anything above, so there is also a subcooled liquid. So next one, a gas mixture at 20 degrees Celsius. Any doubts in the previous one? Okay. So a gas mixture of 20 degrees Celsius, 125 kilopascal, is 50% nitrogen, 30% of water, and 20% oxygen on a mole basis. Find the mass fraction, the mixture gas constant, and the volume for 5 kg of mixture. So you have given a mixture of nitrogen, water and oxygen, just like air. So this is all given in terms of mole basis. You need to find out in terms of mass. So these are mole fractions. So 0.5 moles of nitrogen. If you take 1 mole of this mixture, you have 0.5 moles of nitrogen, 0.2 moles of oxygen and 0.3 moles of water or water vapor. Now we need to find this in mass fractions and also find out mixture gas constant and the volume occupied for a 5 kg of mixture. So let's see how to solve this. So first is in terms of mass fraction. So mass fraction can be expressed as so your mole is nothing but your mass by molar mass or molecular weight, mass by molar molecular weight. So you can write mass as your mass fraction into molar mass. So substituting the moles in terms of mass in terms of moles and molar mass, this is what you get. So Y is your mole fraction into molar mass of that component divided by summation of product of your mole fraction into molar mass. So that gives you mass fraction. So first the summation of mole fraction into molar mass is your molar mass of the mixture or the molecular weight of the mixture. So for that we know the values. So first is nitrogen, the molar mass is 28. This is in term this is of 0.5 mole fraction. So 0.5 into 28 plus 0.3 is water into the molar mass of water is 18, H2O, O is 16 plus H2 is 2, so 18 plus 0.2 of O2. So O2 16 into 2, 32. So we get 0.2 into 32. So summing it up, we get the molar mass of mixture to be 25.811. So using this, now we can estimate the mass fractions. So the mass fraction of nitrogen will be 0.5 into 28, which is 14. 14 divided by 25.811, which gives you 0.5427. So this is your mass fraction. Then water vapor similarly is 5.405 divided by 25 gives you 0.2094, and oxygen to be 0.2479, and if you add this all up you should get 1. So and if you add that up you will get 1, since these are all fractions. So mole fraction was all in terms of moles. Here we have found out in terms of masses. So this says that if you have 1 kg of this mixture, you have 0.5427 kg of nitrogen, 0.2094 kg of water vapor, and the rest is oxygen. So R mix is R divided by the universal gas constant. So it's not R minus, it's R bar. There's a it's been shown as R minus here, some version problem. So R universal gas constant divided by mass of molar mass of the mixture. So universal gas constant is 8.3145 kilojoule per kilomole Kelvin divided by your molar mass, which is 25.811. So this gives you the gas constant for the mixture, which comes out to be 0.3221 kilojoule per kg Kelvin. Now since we know the gas constant, we know the pressure and temperature, and also the mass. So which is given 5 kg. So for a given pressure and temperature, so 125 kilopascal and 393.15 Kelvin, we can estimate the volume. So applying ideal gas equation, so PV is MRT. You can use NRT also, but then you have to find moles, and R will be universal gas constant. So you be careful there. Here mass, so you have to use the gas constant. So V is MRT by P. So mass is 5 kg, R we have found out to be 0.3221, and temperature is 393.15 divided by 125 kilopascal gives you 5.065 meter cube. So that's your volume occupied for 5 kg of mass. So any questions? Because this, if you see, this is somewhat similar to air. So air also, if you see, the density is 1. So your volume occupied per liter is similar to that. Okay, then we'll move to next question. Next question is refrigerant R407 is a mixture of 23% R32, 25% R125 and 52% R134A on a mass basis. So these are all refrigerants. So R407 is also is a refrigerant, and similarly R32, 125 and 134A are all refrigerants. So these are a blended mixture of this composition. So these are mixed in this proportion, 23% by weight of R32 and then 25% by weight of 125 and 52% is by weight of 134A. In that proportion it is mixed to make this refrigerant R407. We need to find out the mole fraction of this refrigerant, the components in this refrigerant, and the mixture gas constant, and similarly the mixture heat capacities of this refrigerant. So how do we do this? So the molar mass is given. So the Ci is your mass fraction. So R32 is 0.23, R125 is 0.25, R134A is 0.52, and similarly the molar fractions are 52. Molar mass is 52 for R32, 125 is 120, and 134 is 102. So with this, now we can estimate the moles for each of the gases present. So if we assume 1 kg of R407 refrigerant, in that case we will have 0.23 kgs of R32. So that will give you 0.23 divided by 52, which is 0.004421 moles of R32. So this is moles. Ci by Mi is the mole. Similarly, R125 you have 0.002083 moles of R125 and 0.52 divided by 102.03 0.005051 moles of R134A. So if you sum it up, we get 0.0116 moles for which is equivalent of 1 kg of this refrigerant. So 1 kg amounts to 0.0116 moles of R407. So we know the total mole and we know the individual moles, so we can find out the mole fractions, which is nothing but your individual mole divided by the total mole. So that will give you 0.381 is the mole fraction for R32. So and 0.00208 divided by 0.0116 is 0.18, and similarly for R134A is 0.439. So these are the mole fractions. So once we know the mole fraction, now we can estimate the mixture gas constant. So R mix is your mass fraction into the individual gas constants, or we can straight away find the molar mass just like what we did in the previous case, and you can divide it by universal gas constant. That's the other way of doing it. So R mix is summation of Ci into Ri. So 0.23 is R32 into the gas constant of R32 is 8.314 divided by your 52.024. So that's what is being done here. So 0.1598 plus 0.25 is for 125 into the gas constant of R125. Similarly 0.52 into gas constant of R134A. So that gives you the gas constant for the mixture 407, which comes out to be 0.09645 kilojoule per kg Kelvin. And similarly we can do it for Cp and Cv. So constant versus specific heat. Cp is again summation of your mass fraction into Cpi. So this is in kilojoule per kg Kelvin. If it is in kilojoule per kilomole Kelvin, you should be careful. You should be using the mole fractions and not the mass fractions. So Cp can be expressed in terms of kgs, kilojoule per kg Kelvin, or kilojoule per kilomole Kelvin. So based on units, you need to be careful which fractions to be used, either mass or mole. If it is in kg, mass, kilomole, the mole fraction. So similarly, doing summation of Ci into Cpi, we get Cp as 0.8298 kilojoule per kg Kelvin, and Cv is a summation of the similar case, mass fraction into individual gas specific heats, that gives you 0.7334. Or the other way of doing it is you know Cp of the mixture and R mix, you can find out Cp minus R. So with this one more question, the adiabatic index, right? You can find adiabatic index using Cp and Cv. How will you find for mixture? Can you use the summation of Ci into gamma I of individual gas this thing, or how will you find it? So the answer is you cannot directly calculate adiabatic index like summation of mole fraction or mass fraction into adiabatic index. That cannot be done. What you need to do is you can estimate the mixture specific heats for constant pressure and constant volume, and then divide Cp by Cv. That's how you will get adiabatic of mixture. That's how it has to be done. So moving on to next question. At a certain point in a coal gasification process, a sample of the gas is taken and stored in a 1 liter cylinder, and analysis of the mixture yields the following results. Components are hydrogen, carbon monoxide, carbon dioxide, and nitrogen. In percentage of mass basis, you have hydrogen 2% and carbon monoxide 45%, carbon dioxide 28%, and nitrogen 25%. So you need to determine the mole fraction and total mass in the cylinder at 100 kilopascal and 20 degrees Celsius. How much heat transfer must be transferred to heat the sample at constant volume from the initial state of 100 degrees Celsius. So we have seen some similar problems the previous case. Try solving this. I'll give you some couple of minutes to solve. This is similar to what we did in the previous two examples. The first is straight away. The first part is straight away you can directly estimate mole fractions, and the mass also we have seen, and we have to estimate using the ideal gas equation, pressure, temperature, and so on. And second part, question heat transfer, you need to find out since it is done using constant volume, you need to find out CV first to estimate the heat transfer. So let's see how to solve this. So first, just like the previous case, uh, for each of the cases, we know the mass fraction. So assuming the total mass is 1 kg, so each will have the respective mole fraction as the kgs. So H2 will have 0.02 kg, CO will have 0.45 kg, and carbon dioxide 0.28 and nitrogen 0.25. And we know the individual molar masses of each of the gases, so we can estimate the number of moles. So the number of moles, the total number of moles will be 0.02 divided by 2 for hydrogen, 0.45 divided by 28 for carbon monoxide, and 0.28 divided by 44 for carbon dioxide, and 0.25 by 28 for nitrogen. So that will sum out to 0.041268 kilomole per kg. So for 1 kg of the mixture, you have 0.041268 kilomoles of the gases. So now the molar mass. So the molar mass will turn out to be this is in terms of mass fraction. So mass divided by molar mass. So 1 divided by summation of mass by molar mass, that will give you molar mass of the mixture. It will come out to be 24.232 kilojoule kg per kilomole. So that is the molar mass of the mixture. So and the mole fractions will be, you can find out using your mole divide by mass divided by mass fraction divided by so the simplest way is you have found out the total number of moles. So that divided by total mole fraction will give you the individual mole fractions. So that's the easiest way to do. And then R mix is R bar universal gas constant divided by the mass of the mixture. Divided by the molar mass of the mixture. So that comes out to be 8.314 divided by 24.2 comes out to be 0.34312. And R mix we found out then using ideal gas equation, the mass is PV by RT. So 100 kilopascal into 10 power minus 3 for 1 liter divided by R is 0.34312 into temperature is 293.15. This gives you 9.942 in 10 power minus 4 kg. This is for mass occupied in 1 liters of the gas. Next is CV of mixture. So that is summation of mole fraction into your CV of the individual gas. So that comes out to be 0.9056 kilojoule per kg Kelvin. So CVs will all be given, even molar mass is not given, you can calculate molar mass. Then Q, the heat transferred will be mCV delta T. So if you can, even in this case, if you apply first law, there is no work done. So the delta U is Q minus W. So W is 0, delta U is Q, and TU you can write it as mCV delta T. So mass we have found out 9.942 in 10 power minus 4. CV is 0.9056, and temperature differences, this is heated from 20 degrees to 100 degrees. So 100 minus 20. So that gives you 0.072 kilojoule. So any question? Okay. So then moving on. A flow of 1 kg per second of argon at 300 Kelvin and another flow of 1 kg of CO2 at 1600 Kelvin, both at 150 kilopascal, are mixed without any heat transfer. What is the exit temperature and pressure? So you have two gases mixing, both are at same pressure but at different temperatures, and the mixture is coming out. We are assuming there is no heat transfer outside. So it's an insulated mixing chamber. So what will be the temperature and pressure? So since ideally there should be no pressure drop, since both are at same pressure. So you assume that mixing chamber will also be in that same pressure. So output will also be at 150 kilopascal. We need to find out the temperature. So what will happen is CO2 is coming in at a higher temperature, which is at 1600 Kelvin. So this will heat up argon, and so in the process it will cool down and argon will heat up. So CO2 temperature will drop and argon temperature will increase. So both of individual internal energies will change, and we will see how to solve that. So first, there is no pressure change. As a simple case, there will be no pressure drops. Ideally it will be 150 kilopascal. So if we write an energy equation, so the argon internal energy change is equal to, I think this has to be done using flow system. It's not covered. Okay, I'll skip this question. I'll put it again 2 weeks later. I think that's where the flow systems is considered. I think by mistake I have put this question here. Since we have seen only first law for an closed system, so we'll stick to questions on those. Flow system questions we'll see in coming weeks. So moving on to next question. A rigid insulated vessel contains 12 kg of oxygen at 200 kilopascal and 280 Kelvin, separated by a membrane from 26 kg carbon dioxide at 400 kilopascal and 360 Kelvin. So the membrane is removed and the mixture comes to a uniform state. Find the final temperature and pressure of the mixture. So what you have is a insulated vessel with with a partition with one part of containing 12 kg of oxygen at 200 kilopascal and 280 Kelvin. And the second part contains carbon dioxide at 400 kilopascal and 360 Kelvin. So both are at different pressures and temperature. Now what happens is this partition is removed, this membrane is removed. So the mixture will mix with the gases will mix and will form a mixture, and they say the mixture comes to a uniform state. So what will be the final temperature and pressure of the mixture? So what we'll first do is we know mass, pressure and temperature for each of the gases. So we can estimate the volume occupied by each of the gases, and using those we can find volume will be equivalent to your mole fractions. So volume fraction, using those we can find out the mole fractions. So first is the total mass. So we can find out mass of oxygen plus mass of carbon dioxide. So 12 plus 26 gives you 38 kilojoule, kg. Since this whole process is in a closed system and there is nothing going in and going out, so the work done is 0, there is no heat transfer to the surrounding, so delta U should be 0. So U2 minus U1 is 0. So your initial internal energy is equal to the final internal energy. So rearranging this, we get m naught Cv del T2 minus T1 plus m of carbon dioxide Cv of carbon dioxide into T2 minus T1 of carbon dioxide. So we know mass, we know Cv, we can estimate temperature. So for initial state, so Cv of oxygen is 0.662 kilojoule per kg and Cv of carbon dioxide is 0.653 kilojoule per kg Kelvin. So we know this, we know mass, we know the initial temperatures. So we can estimate T2. And what else is asked? And the final pressure is also have to be found out. To find out the final pressure, now we'll find out the initial volumes occupied by each of the gases. So initial volume is of oxygen is 4 mRT1 by P, assuming an ideal gas equation, we get 4.3646 meter cube. And similarly for carbon dioxide, mRT1 by P, we can estimate volume of carbon dioxide to be 4.4203 meter cube. So R mix is summation of mole fraction into your gas constant. So mass fraction, we can we know individual mass, we know total mass, so that will give you the mass fraction. So 12 into your gas constant of oxygen plus 26 into gas constant of carbon dioxide divided by the total mass, that gives you 0.2113 kilojoule per kg Kelvin. So the total volume will be your individual volumes occupied by the gases. So that comes out to be 8.7849 meter cube. And using the ideal gas equation, we find that P is mRT by V. So R is for the mixture. Now we are assuming the total mixture as ideal gas. Using this, we need to find out temperature, and the temperature, as I told previously, from the U2 equal to U1 equation, the only unknown is temperature. So you get temperature as 334.5 Kelvin. Substituting that here, we get pressure as 305.7 kilopascal. Any questions in this?
Hello, sir. Good evening.
Yeah.
So I have a question about a thermodynamical subject. Can I ask here?
Yeah.
Whenever means from the way I start loving this subject, I have a question that what is the reason to study thermodynamics and what the purpose means what industry need from a thermodynamic engineer? Can you explain here?
So the voice was breaking, but what I understood is what is the role of thermodynamics? That's what you want to understand.
No. What is the reason to study the thermodynamics, or what industry requires from a thermodynamic engineer?
See, whatever system you take, you can do an see, you need to build better systems, right? If you take an engine, you try to run a car, you are building an engine. How do you know how the engine is performing? How will you compare whether this engine is better, or how will you know how much can you improve it? This all comes from thermodynamics. So the idea of the laws stated, so is all was derived on the principles of heat engine for making better heat engines. The idea of what you learn, a Carnot cycle or an ideal reversible cycle, reversible engines and so on, these all principles came saying how much can you improve these engines. So what is the best performance, and you put a benchmark there and you try to improve there. And if you need to analyze a system or power plant, you are trying to reduce your energy consumption or electricity bill also, whatever. How will you know which part of the system is consuming the more energy or less energy, which is more efficient, or how can you improve this? This all ultimately breaks down to thermodynamics.
Oh, okay, sir. Thank you.
Okay. So this will also go deeper when you go over the weeks. You also learn about the second laws and so on. That will give you an idea of estimating losses, and also give you a second law efficiency, which you define. That also will give you an idea. You can compare. It's an now it's like an of an independent quantity where you can compare with a constant benchmark and not an individual like an apple to apple comparison. You can that kind of benchmark and kind of will be given by those laws, so which we will be learning in the later stages. So now what you are generally dealing is need to understand how energy is being interacted, how it is getting transformed, and so on, doing a total energy balance in the system. So this first law states only the balance, how what is coming in, what is going out, and how it is getting converted and so on. So this the later part of which will define how useful is that and so on. Okay.
Thank you, sir.
With that, next question. A piston cylinder device contains 0.1 kg of a mixture of 40% methane and 60% propane gas by mass at 300 Kelvin and 100 kilopascal. The gas is now slowly compressed in an isothermal process to a final pressure of 250 kilopascal. Show the process in a PV diagram and find both the work and heat transfer in the process. So the first case is we have a mixture which is methane and propane, and by mass this is by mass fraction, and it is at temperature of 300 and 100 kilopascal. First it is being slowly compressed in an isothermal process, so to 250 kilopascal. So we are showing it in PV and TS diagram. So TS you will see later, you can see the TV diagram. So one this at lower higher volume, and the pressure is at 100 kilopascal. You are compressing it isothermally. So this is how the process will look, 1 to 2. And similarly in a TV diagram, it's a constant temperature process, isothermal. So for isothermal process, your the process equation is PV equals constant. So with that, applying the first law equation, so you get mu2 minus u1 is q minus w. So for this now finding out work is integral p dv. if you integrate P as C by V and integrate it, what you get is MRT ln V2 by V1. So you need to find out the gas constant of the mixture. So again, going back is mass fraction into gas constants of individual component. So the gas mixture gas constant is 0.4 into your methane gas constant plus 0.6 into your propane. So that comes out to be 0.3205 kilojoule per kg Kelvin. So substituting that in the work expression, we get MRT ln V2 by V1 or ln P1 by P2. So since we know the pressures in this case, we will use the second expression MRT ln P1 by P2. So what we get is 0.1 into 0.3205 into temperature is 300 into ln 100 by 250, which comes out to be 8.81 kilojoules. And this is negative because the work is being done in compressing the gas. So we know work, since we know it's a constant temperature, U2 minus U1 will be 0. So CV delta T, so that will be 0. So your Q will be equal to work done. So your Q is minus 8.81 kilojoule. So moving on to next question. A closed rigid container of volume 0.5 meter cube is placed on a hot plate. Initially the container holds a two-phase mixture of saturated liquid, water and saturated vapor at P1 is 1 bar with a quality of 0.5. After heating, the pressure in the container is P2 equals 1.5 bar. So indicate the initial and final states on a TV diagram and determine A, the temperature in degrees Celsius at states 1 and 2, the mass of vapor present at states 1 and 2. If heating continues, determine the pressure in bar when the container holds only saturated vapor. So what is this case? So you have closed rigid container. So this is like similar to your pressure cooker, for example. Just that you don't have that vessel at the top where your gas is releasing out. So you have a container, closed container, which you are heating it. Initially it has a two-phase mixture, liquid and water, and the initial saturated vapor is 1 bar and quality is 0.5. So that means if you have 1 kg of water, you have 0.5 kg of water and 0.5 kg of water vapor or steam. So after heating, the pressure in the container is now 1.5 bar. So we need to show that in a TV diagram and determine the temperature in degrees Celsius at state 1 and 2. And if the heating continues, determine the pressure in bar when the container holds only saturated vapor. So that's what it does. Let's see how to solve this. So this is how the process in a TV diagram looks. So in a TV diagram, you are initially at 1 bar pressure and at 0.5 vapor fraction, and then since it's a closed container, your volume will remain constant or your specific volume will remain constant here. So you are going vertically up. So from 1 the pressure has increased to 1.5 bar, so it's at state 2 here, and then heating it again when it's fully saturated vapor, it is at some pressure P, which we have to find out from the question. That's what been asked. So this states we have to find out. So first what we know is your volume is constant. So first we will find out what is this specific volume at state 1. So since we know that vapor fraction is 0.5 and we can estimate your specific volumes corresponding to 1 bar, saturated gas, vapor and saturated liquid specific volumes. and using that we can find out the specific volume at 1. So similarly, I'll just show one example of how to estimate from the chart. So going back to the chart, this for 1 bar, so that is 0.1 megapascal. So 0.1 megapascal. So you see there is a with pressure. So since we are looking at pressure, 0.1, your saturation temperature is 99.6. So that is your T1, and the density column or we need volume. So we can straight away go to the volume column. So 0.1, these are the volumes. This is 1.04315 and 1693.9. This in centimeter cube per gram. So those are the specific volumes of the saturated vapor and saturated liquid. So for the mixture, specific volume will be your liquid specific volume plus X into Vg minus Vf. So substituting the values here, so we got Vg as 1694 centimeter cube per gram. So converting that into meter cube per kg, so 1.694 we get, and Vf is 1.0432 in 10 power minus 3. So substituting the values, V1 comes out to be 0.8475 meter cube per kg. So now at state 2, we know the specific volume, we know 2. So we'll similarly do the same equation. We'll estimate, find out the specific volume of saturated vapor and saturated liquid, and using the same expression we can find out X. So here in this case, if I see your specific volume of liquid is 1.0582 in 10 power minus 3, this is less than your specific volume 0.8475. So that says it is lying above your saturated liquid condition, and your saturated vapor volume is 1.59 meter cube per kg, which is less greater than the specific volume V1. So that says it's still in 2-phase region. If the specific volume would have been greater than 1.59, that says that it has entered the superheated region. Since this is lower, it is still in 2-phase region. So that's why state 2, it is lying between your saturated liquid and saturated vapor. So corresponding to this temperature pressure, the corresponding saturated temperature from the same table, the saturation temperature will be the temperature at state 2. So that is 111.4 degrees Celsius. And we can estimate X also. The same expression we can use. The only unknown will be X. So V1 will be we know 0.8475, and VF1 and VF and VG we know for state 2. Substituting that we can find out X. So that will give you the vapor fraction at state 2. So X2 is 0.731, and similarly mass of vapor present, if they ask the mass of vapor present at 1 and 2 is asked. So for finding out mass, we know volume is 0.5 meter cube, the closed vessel volume is given. So the total volume divided by specific volume will give you the mass. So that gives you 0.59 kg of the total mass. So the mass of gas will be your vapor fraction times the total mass. So 0.5 into 0.59 is 0.295 kg. So that is the mass of the steam which is present at state 1 initially before heating. Similarly, at state 2, you have found out your vapor fraction to be 0.731. So your mass of steam will be 0.431 kg. So we see the mass has increased. So the total mass is 0.59, out of which 0.431 is your vapor. See, the vapor fraction also returns 1, it is fully saturated vapor. So we are heating there. By heating it more to state 3, we want it to be fully saturated vapor. So in that case also your volume, specific volume will still remain same of 0.8475, which was at the initial V1, because you are a constant volume process. So 0.8475. So again going back to the chart, we need to find a pressure where you get 0.8475 of vapor. So if you see here, this is in centimeter cube per kg, so divide by 1000, which will give you the same. So you are lying between 0.20 and 0.21. The specific volume, we need 847.5. We need 847.5. Here at 0.2 it is 885.68, and at 0.21 it is 846.14. So it will lie between, somewhere in between 0.20 and 0.21 megapascal. So we'll do an interpolation there and we can find the pressure. So that will come out to be 2.11 bar. So next question. So next question, water contained in a piston cylinder assembly undergoes two processes in series from an initial state where the pressure is 10 bar and the temperature is 400 degrees Celsius. So process 1, 2, the water is cooled as it is compressed at a constant pressure of 10 bar to the saturated vapor state. Process 2, 3 is the water is cooled at constant volume to 150 degrees Celsius. Sketch both process on a TV and PV diagrams. B, for the overall process determine the work. C, for the overall process determine the heat transfer. So we'll see how to solve this. So first is, we have initially the water at 10 bar and 400 degrees Celsius. Next, what is being done is this water is cooled while it is being compressed to 10 at a constant pressure of 10 bar. So that it is coming to a saturated vapor state. Then this is being cooled at constant volume at 150 degrees Celsius, to temperature of 150 degrees Celsius. So this is how the process will look. So in the PV diagram, the PV dome, so initially at pressure of 10 bar and 400 degrees Celsius, it is at superheated state, which is compressed at constant pressure. So coming to state 2, which is at saturated vapor, and then cooled to state 3 to 150 degrees Celsius. So corresponding to that 10 bar, your saturation temperature is 179.9, and corresponding to 150 degrees Celsius, saturation pressure is 4.758 bar. And this is how it will look in TV diagram. So from 400 degrees Celsius, you are coming to state 2 and then cooling it to 150 degrees Celsius. So again, the first one, since it's a constant pressure, so there will be no work done, so that will be 0. Second case work is integral 1 to 2 PdV. sorry, second, since your volume is constant, your work will be 0. The first case is integral p dv. So your work done will be W by m is p into specific volume differences V2 minus V1. So we need to find out the specific volume of saturated vapor at state 2 and the initial specific volume from the steam table, which comes out to be at 10 bar and a temperature of 400 degrees Celsius. Your specific volume is 0.3066 meter cube per kg, and similarly your specific internal energy is 2957.3 kilojoule per kg. Next is the specific volume at state 2 is a saturated vapor value at 10 bar, and V2 is 0.1944. So with this we can find out the work done for process 1 to 2. So P delta V comes out to be 112.2 kilojoule per kg, the negative sign, since it's compressed, you are doing work. So if we do an overall energy balance, so m into U3 minus U1 equals Q minus W. So by rearranging, we get Q is U3 minus U1 plus W by M. So we know U1. So once we find out U3, we can find out the total heat which is removed from state 1 to 3. So since the exit state is 3 is at 2 phase, can find out the dryness fraction using the specific volume we estimated at state 2 and the saturated specific volumes of liquids and liquid and vapor. So we'll get X3 as 0.494, and similarly U3 is the internal energy of liquid plus vapor fraction into your internal energy of saturated vapor minus saturated liquid. This to again a similar reading from the steam table. We get U3 as 1584 kilojoule per kg. So Q is change in internal energy plus the work done. So 1584 is the internal energy at state 3 minus 2957.3 is at state 1 plus the work done, which is minus 112.2. So this comes out to be minus 1485.5 kilojoule per kg. So this says that this much amount of heat which has been removed from state 1 to 2, so 1 to 3, the whole process. So with that I have finished what I have prepared for today. So next week we will see some more problems with two phase and first law. And continue the session next week, Tuesday. Thanks for joining.